Thank you for coming to our North Houston Space Society meeting. This is our May 20th meeting. Normally we meet in person at the Barbara Bush Library, and definitely looking forward to both getting a haircut and resuming those meetings. I normally don't wear a cowboy hat, but that was better than full mad scientist. Um, and then
Well, for this group, maybe not.
maybe not. I know I should, yeah, I should think that through a little bit more. You know, and we did so well in preparing for our last meeting about Zoom bombing. It almost seemed theoretical at this point, and that we had everything locked down the way that we needed to. Our vision is safe meetings that are free and welcoming to good people. But in addition to that, we would like to, um, you know, our vision as a society is people living and working in thriving communities beyond Earth, but then also using the vast resources of space to dramatically improve the betterment of Earth. And the interesting thing is, if you look at Elon Musk, and they both kind of exemplify the two aspects of this. Like Elon Musk sees his goal as creating the first city on Mars, and Jeff Bezos sees his goal as creating the infrastructure that allows for us to move all of the Earth harming activities into space, and then also use space for energy production and actually preserving the Earth to be more of a kind of a garden spot. So it's really kind of interesting looking at those two personalities and their different goals with relation to space. So if you share this vision of people going off into other parts of the solar system and exploring space, and then also using the resources of space to a better Earth, there's lots of things you could do. One is kind of like learning about that yourself. The second thing you could do is talking about it and sharing it with other people. You could go work in the space industry. You can do outreach, and you can do kind of activism and engineering and thinking. But a really small step that you could do today might be to actually join our mailing list, which can be done from our website, northhoustonspace.org, right there on the left-hand side. And also, another thing you might consider doing is actually joining the National Space Society. It's only $20 for the first year, helps to support the group. Several things I wanted to point out is that this meeting is being recorded, and apparently now also afterwards, before it's posted. And I just wanted to point out that by default, we stop all video for people coming in, so there's no surprises, but if you wanted to turn on your video, you could. And with that, I'm going to pass it over to Greg. And let me make sure you can unmute yourself, okay? So you should be good.
So, talking about space news here, actually a comment on this particular image. This is one of the original, or maybe the very first, Apollo 11 shot of Earthrise. Kind of appropriate because a lot of the news right now is actually focused on getting back to the moon. It's been a long time since we've been able to take pictures of that. So, but before getting to the moon stuff, talk a little bit about space station news. This is all things that have happened since our last meeting. So they happened during the month of April. There was a crew sent up, one American and two Russians, launched from Kazakhstan. This should be the last one among the crewed launches that are launched from there. We should be able to start doing that fairly soon. So if everything goes well, we won't be seeing so many of these pictures anymore, although dramatic though it is. Other thing I'll comment on is that we love these kind of pictures, powerful rockets taking off. We tend to forget that actually there's the other end of that, is that during the same month, three astronauts came back, and they just basically drop in a flaming capsule, bounce around on the ground a bit in Kazakhstan, also get picked up by people in helicopters. That's actually the return crew. And yes, that little small compartment is what the three people had to squeeze into. So that's one launch, one return, and actually there was a cargo launch as well, again, from the Russian Kazakhstan site. So those were things that happened related to the space station. Now moving on to lunar activities, things are really heating up there. NASA issued a new contract here to a company called Maston Space Systems. I think they're Californian, for robotic lunar landing in 2022. And what it is, the way this works is kind of a public-private partnership kind of thing. NASA pays for the service, so they're paying 76 million, and this is really a phase one kind of thing, but they're paying 76 million to deliver, a set of instruments to the moon's south pole in this particular case. In this case includes a rover and a robotic arm and a variety of experiments. They are actually the fourth company in this program, which is called Commercial Lunar Payload Services, or CLPS. I'll get to the others in a minute. Anyway, this mission would, if it succeeds, would be the first to softly land at a lunar pole. Actually, the Israelis had tried that not too long ago, and the Indians too, I think, but it didn't land softly enough to survive. Payload of this would be 80 kilograms, but actually in their lander, they have room for more. So they're actively trying to sell space. And I think they might have even sold some to others. I'm not sure what for. They haven't yet announced how they're going to get there. Who's going to launch them, whether it's, SpaceX or somebody else. Now, you may think 2022 is pretty early, actually, for getting back to the moon, because we're thinking in terms of the human landings, which could be as early as 2024. But actually, 2022 is not the first. We have 2021 from a Houston-based company called Intuitive Machines. About the same amount of money. NASA is spending $77 million to pay them to send a robotic lander delivering some science instruments. This particular one, and it's the same program. This particular one is not going to a pole, it's going to somewhere closer to the equator, but they're landing near a narrow valley, which is probably a collapsed volcanic lava tube, and to explore that area. That one they have announced they'll be using SpaceX with the Falcon 9 rocket. It has about a 100 kilogram payload. And this is just for the sake of completeness. There's no recent news here from Astrobotic, which is a Pittsburgh-based company. But they might have actually been the first to get these kind of contracts. And they got about the same amount of money. They got the most at 79.5 million for a robotic lander to land and deliver payloads. It has about a 90 kilogram payload. They're the ones that actually have published a rate. If you have 1.2 million, you can send a kilogram to the surface of the moon. And in fact, they'll supply you with a certain amount of power depending on how much you spend with them. But they guarantee you power and a variety of other services along the way. So it's kind of interesting. It's a lot more expensive than going to low Earth orbit, but all of a sudden it's not billions and billions and billions of dollars to get something to the moon. So things are definitely changing with new space. Now moving on to the human area, NASA has announced funding. They finally made their choices basically for what they're calling the Human Landing System, or HLS. A whole set of new acronyms come out every month, of course. And now we need to learn this one, HLS. And it's about $1 billion split among three companies. They've been working to narrow it down for a while. It's part of the overall Artemis program, which is in general trying to get back to the moon. And the line is go back to the moon to stay this time. This is just phase one funding, the last 10 months. And then after that, there's going to be evaluations to decide how to proceed. And maybe they'll whittle down one of the companies. And between the three companies, that's about $1 billion. The entire project would be about 18.4 billion through the end of 2024. And I think I've seen several different figures on it. It might reflect what time period is involved. And what's interesting about these programs is that each contractor really does have to provide private funding for design and development. And I'll make a side comment that why we need to be space advocates is that there are actually quite a few people in Congress who really don't believe that the private companies should even be in space in the sense of not owning anything and providing services and that sort of thing. They really believe the government should just own everything and control absolutely everything. So actually all of these programs have a certain risk when it comes to that. I'm talking about both the robotic ones and the human ones. This particular picture, this is an Orion spacecraft. And what's interesting is the original NASA plans, of course, were to link up with the Lunar Gateway, which was like a mini space station orbiting the moon. They dropped that to the short-term plans so that somehow or other, one way or another, astronauts would go up in this Orion spacecraft launched by the SLS. They're the large launcher, and then it will meet up with the lunar lander in some way. And apparently, it's not really that completely specified yet just how that's actually going to happen. So there's still some gaps in the plans on this. So the three companies, here's some visualizations of what each of their landers look like. Blue Origin got the biggest chunk of money at 579 million, and they're partnered with Lockheed Martin and with Northrop Grumman. I take this as kind of a good sign that Jeff Bezos is really figuring out how to play the political game. He knows how to tie, he now has figured out he really needed to tie in with existing players and probably couldn't just do this all alone. So that's probably a definite sign of some kind of a change in their programs. So in all of these, what's interesting is you look at the size of the landers. The one from Blue Origin and the one from Dynetics, they're kind of comparable in size. SpaceX is considered kind of the outlier here. You can see the people in these pictures if you look closely enough, or at least I hope you can on your screens. The SpaceX, they're talking about using Starship. Now that's a huge thing. That could carry a couple hundred tons. There's a little picture of an astronaut down there that you can barely see by my cursor there. That one, NASA has said that's sort of an outlier. It's a long shot, so they're not funding it as high. They're only giving them the 135 million. But they also say, well, it could be a real game changer if they really figure out how to do this and can do it in time. So that's why they are funding it to some extent, because they would just do pretty much one launch straight to the moon, and be there with huge quantities of material. I guess I kind of glossed over Dynetics, which was the other partner. They're partnered with another company out of California called Sierra Nevada, 253 million. So 3 different landers. Probably all 3 won't all go ahead. Something will be dropped along the way. But they are funding it, for phase 1 to see how they go. Just a quick update. We've talked before about the Starlink communication satellite project from SpaceX. And this is the one that'll have thousands, 12,000 satellites, or now they've actually applied for another couple thousand to provide internet service worldwide. These are visualizations of their, how each satellite would communicate with some area over Earth. Over here on the left is what they would look like. But there's been a lot of criticism. The astronomers have been really worried about the brightness and the number of satellites, saying that all their time-lapse photos of the skies are pretty much going to be ruined. And so it seems SpaceX has actually listened, and they tried black paint over some of the areas, and it turned out that actually causes too much thermal stress. The black paint actually absorbed more sunlight, and it didn't work out that well. It did reduce some of the light. So they're doing something different now, and they're planning on putting this apparently on all of the upcoming satellites. They're going to have some foam that the radio signals, for internet communication can get through, but it won't block those, but it will block the light. And so that's one way they're solving the problem. And the other one is that they're going to be more careful about the orientation of the satellites. And so, for instance, there's always several phases on their launches. The first phase, they just get up into a low orbit. Then as they, once they're working, the solar power is working, they turn on their ion thrusters and they go up to a higher orbit. In the process of doing that, what they're going to do is make sure that, and this is what they're saying, is that they're going to kind of orient themselves so that towards the sun in a lot of ways, so that basically there just won't be that much reflection off of them. And then they're going to tilt them at a different angle when they're in their permanent orbit. In their permanent orbit, they call that the shark fin. It looks kind of like this drawing at the top here, where Earth is below it, and then the fin of the solar panel sticks up. And they're going to angle it in such a way that supposedly it won't reflect as much. So this is their attempt to address these concerns. Like I said, certainly a lot of astronomers are pretty upset. So we have a part of the meeting where we could guess how many launches have there been since the last meeting. And for the legal beagles here, the fine print says, yes, that does include failed launches, which happens to matter this time since there was one. Anybody want to take any guesses?
3.
And I also
the problem
made
is
it.
nobody can unmute. I guess that's right. That's not.
Yeah, people can unmute unless they just happen to be unmuted at the time that I turned on that option. But you put it in the chat room to go to the host. So I think Greg, Lee, and myself could see the answers. So Vito said 3, William said 5. Any other choices?
Okay, well, I won't keep you in suspense any longer. Actually, the answer is 6, counting one
Ah,
failed one. So we had some pretty close. We had some near winners there. And we've already talked about a couple of them already. So of course you had a little bit of a leg up. There was the Soyuz launch of cargo to the ISS. There was that batch of Starlink satellites. They go up in batches of 60 at a time. There was one launch of those. The one that I didn't see coming was the one from Iran. They in the past have tried launches quite a few times to launch military satellites. And this is the first one that actually succeeded, as far as I know, or at least it's the only one that recently has succeeded. So they have their own booster called a Quasid. I don't actually know how to pronounce that. And the satellite's called the Newer. So at least they actually do have one up there now. I had to go searching for their flag. Hadn't seen that before. The one that failed was launched by the Chinese. Was actually for an Indonesian use of an Indonesian company, the Palapa communication satellite. That one failed. And then of course I'd already talked about getting crew up to the ISS for the April 9th launch on Soyuz. I believe that's it. Now we are going on to the featured speaker, Lee Hutchinson. He is a senior technology editor at Ars Technica, and I don't know if everybody's familiar with Ars Technica, but it's kind of like a Wired in a lot of ways. It's technology oriented, but it covers, it touches on pop culture and lots of other things too, and gaming and everything else. So it's a fairly interesting site. He oversees story development for the gadgets, automotive area, IT, and video sections of Ars Technica. And he also writes longer pieces about manned spaceflight and gaming, which ties into what he's talking about today, which is some research he's done about what people did during Apollo. All those people sitting at those mission control consoles, what were they doing? Well, he's going to tell us about that. He does have an extensive background in enterprise storage and security. He did spend a decade at Boeing as an enterprise architect, and then had moved on to EMC and Symantec before, I guess, he discovered his true calling in Ars Technica. Now, these two pictures I put to the right, actually, he didn't provide those. I just found those on the internet. They appear to both be, normal, approved kind of pictures. I'm not sure if they represent a before and after major life-changing event, or if, I don't know. I'll leave that for him to describe. But I'll turn it over now to Lee.
Thanks, Greg. I can actually tell you the picture on the top is from it's from a couple of years ago when I was doing a piece on the neutral buoyancy lab that was shot in the back in the suit and tool lab section of the NBL. And then the picture on the bottom, you can't tell in the way the picture is, but I'm actually upside, and we're flying inverted. This is in a fallen Gnat, which is a high subsonic trainer aircraft. There's a gentleman named Rick Sharp who flies with the Collings Foundation, and I won a ride in the aircraft at a charity auction. And it was funny because I went in there, I've never really had problems with motion sickness, and so I went in there and I was like, all right, Rick, I want you to, let's go upside down. Let's do all the loops, do everything. And we got in there, and after 2 minutes, I was like, yeah, okay, I'm done. It turns out that when you're sitting in the back and the guy in the front is excited and you told him to do all the aerobatics, that it's super disorienting, and you get real sick real fast, which I did. So we
Okay.
fortunately
so this
backed
also
off
wasn't a
before we
Hollywood.
did anything. What's that?
Sorry. It wasn't a Hollywood style origin story.
No, it was just down at Ellington. The aircraft lives down there, along with a bunch of other really, really cool Cold War era warbirds that the Collings Foundation maintains. They've got an F4 down there. They've got an F100. They've got a bunch of cool aircraft down there. I think it's an F100. So anyway, let me get my screen sharing going here, and I'll get this presentation kicked off. So I also apologize if you guys are going to be, I'll be sharing my screen. So there's a presentation. And if you keep the little camera view up, my eye line is probably going to be all over the place. I've got a couple of different monitors here. So I'm going to have my presenter notes and then the thing I'm presenting. So if you're watching me on the camera, you're going to probably see me doing a lot of this. That's just because I'm trying to read my notes and do this at the same time. Okay, so let me drag this view over here and press the button. And I want to share that one. And I want to go full screen like this. Okay, so I think if I did this right, you guys are seeing my title page. Nathan, is that, and Nathan and Greg, is that correct?
That's correct.
Perfect.
Yes.
Okay. So I'm building very briefly on the intro that Greg gave. My name is Lee Hutchinson. Hello, everybody. I worked in the space industry for just under 10 years, out of college from 2001 through 2010, supporting the shuttle and station programs down at Boeing's Clear Lake campus down here. A few years after leaving Boeing, I wound up at my current job doing media and journalism at Ars. Ars Technica is a science and technology news publication. Greg said it's sort of like Wired. Wired's actually a sister property of ours. We're all owned by Condé Nast, which is this giant magazine conglomerate that owns basically 80% of the magazines you've ever heard of: GQ, Brides, Vogue, Vanity Fair, Wired, all these. It's all Condé Nast. So Wired is a sister publication of ours, and the way that our ad sales people describe us versus Wired is they'll say, if Wired is a biology class, Ars Technica is like the AP biology class. So we like to think we're a little bit more of a discerning, deep tech brand. So I've been lucky enough in my current job to have the opportunity to do a lot of research and writing about Apollo, which is kind of my personal passion. I've spoken with a lot of the folks who are involved in it. We've done a ton of interviews and writing, and over the course of the last several years, I've collected sort of a bunch of cool little bits and bobs about Project Apollo. And so this is sort of a presentation that goes through a bunch of different things that I found that I was really interested in, and I figured that folks who like space might be interested in it also. So here we go. This is going to kind of jump around. It's organized, but it's going to kind of jump around a bit. Oh, and one last thing before we get really going here. There are 2 videos in this. And I normally, play them because I usually do this in person. So what we'll do when we get to the videos, they're both on YouTube. So I'll drop YouTube links. And Nathan can, I think actually if I have presenter power, I can send it in the chat out to everybody. So when we get to the video part, I'll drop the video links in the chat. You can watch the video and I'll pause for the appropriate amount of time, and then we'll come back and continue. So let's get rolling. First, a bit of historical context. There were a total of 9 Apollo missions that left Earth orbit and flew to the moon. And each one of those Apollo missions carried 3 astronauts. Out of the humans who went, 3 of those astronauts were lucky enough to make the trip twice, which is why there's 24 people listed here. And that's Jim Lovell on Apollos 8 and 13, John Young on 10 and 16, and Gene Cernan on 10 and 17. In spite of how grand Apollo seems, when you actually look at the amount of time we had the operational capability to put humans on the moon, and by operational capability, I mean like butts in seats, hardware ready to go, and missions defined, it works out to be almost exactly 4 years, and only 4 years, which feels surprising. But I literally, Apollo 8 lifted off in December of 1968, Apollo 17 splashed down in December of 1972, and that's it. How did we do it? Well, rather than get bogged down into a discussion about the political realities of Apollo, because we'd be here all day, I'm going to keep this discussion centered around technology. We're going to talk about facilities, hardware, and software. Specifically, I'm going to focus up on 3 areas of interest. We're going to talk about the ground, a little bit about mission control. We're going to talk about the rocket, the Saturn V, and we're going to talk about the 2 Apollo spacecraft, the command and service module and the lunar module. And the idea here, especially with the spacecraft talk, is to illuminate a little bit about how complex this machinery really was and why we were able to do what we did, even with technology that seems just hopelessly out of date compared to, modern 2020, 2019 standards. So we're going to start with mission control. Mission Control is located in the Johnson Space Center down in Clear Lake. If you folks haven't been down to visit it, I highly recommend you come down and do it. If you come on some Saturdays, once we get out of quarantine, and you do the tram tour to go see the Saturn V, you'll probably see me because I volunteer on weekends doing Saturn V tours down there. So please come and see me. The Johnson Space Center, JSC, was originally named the Manned Spacecraft Center, or MSC, and it was referred to it that way through this all the way up until the mid-70s. I think the renaming to JSC didn't happen until well into the end of the 70s. And its presence in Texas is kind of an oddity. So after Sputnik in 1957, the government turned to a small academically focused organization called the, you may have heard of it, the National Advisory Council on Aeronautics, the NACA, to research human spaceflight options. And NACA was headquartered up in Virginia. And the original Space Task Group was primarily made up of folks who came from or lived in the Northeast. Things really got going with NACA and the Space Task Group in 1958. And that was the year that NACA was dissolved and rechartered as a full-fledged government agency that you may have heard of called NASA. Over the course of the next few years, as what would become Project Mercury unfolded, there was a lot of horse trading that went on about where to build all of the enormous permanent facilities that NASA was going to need to do more than launch like little tiny one-person Mercury spacecraft. And there were dozens of proposed sites for NASA centers. The proposed Houston site was nobody's first choice, and especially not the Space Task Group folks in Virginia who didn't really want to move, didn't really care for the weather down here, didn't really want to have anything to do with Houston. But it came down to old-fashioned politics. And here I'll quote, this is from, I forget the source, but I've got it noted in here. I'm going to quote A&M historian, a gentleman named Henry C. Dethloff from Texas A&M. He says, quote, "Although the Houston site neatly fit the criteria required for the new center, Texas undoubtedly exerted an enormous political influence on such a decision. Lyndon B. Johnson was vice president and head of the Space Council. Texas 8th District Representative Albert Thomas headed the House Appropriations Committee. Texas 22nd District Representative Bob Casey and Texas 6th District Rep. Olin C. Teague were members of the House Committee on Science and Astronautics, and Teague also headed the Subcommittee on Manned Spaceflight. And finally, Texas 4th District Rep. Sam Rayburn was the Speaker of the House." So Texas sort of had a stacked deck, plus Rice University, as you guys probably very famously know, essentially gave the land to the government in perpetuity for more or less free. This turned out to really be a smart strategic decision. This was a good idea. And one of the big reasons why it was a good idea is because by siting the astronaut office in Houston, you're more or less central to the two coasts where a lot of the Apollo work was going. You had plants in California, in the beaches, Long Beach, Seal Beach, Downey, and all that, where there was a ton of assembly work going on. You had the Kennedy Space Center in Florida at the Cape, where there was all the launch activity going on. You had stuff in the Northeast with Grumman. You had St. Louis and all the stuff going there. And it turns out that by having the astronaut office and a lot of the spacecraft offices headquartered here, it's roughly the same distance to fly to all of those places from Houston. Whereas if you were on the coast, either coast, making a visit out to California might be a transcontinental flight. Making a visit to the Cape might be a transcontinental flight. Plus, at the time, you know, the Cold War was very, very heavily going on. Many of you guys were alive through it. I unfortunately was not. I'm too young. I was born in '78. But a geographic separation of your nation's strategic assets also makes sense. If you separate your mission control from your launch facilities, a single nuclear device can't take them both out. And if it does, then, man, you've got way worse problems than worrying about your space program. Like at that point, like, you know, things are very problematic. So mission control in general refers to the building where the mission control rooms are. And if you folks have ever been on site, you know, this is a picture of Building 30 at the Johnson Space Center, which a few years ago was renamed as the Christopher C. Kraft Jr. Mission Control Center. The actual control rooms go by various names. The shuttle control rooms are called FICRs, for FCRs, flight control rooms. The ISS control rooms are FICRs. In the Apollo era, they were called MOCRs, Mission Operation Control Rooms, and there were two of them, one on the 3rd floor of Building 30 and one on the 2nd floor of Building 30. Almost all the Apollo missions were flown out of MOCR 2, which is the one on the 3rd floor of Building 30. And incidentally, if you go and do the tour today, MOCR 2 is the one that is on public display that you get to see. So if you do that tour, if you're down at Space Center Houston and you do the Level 9 tour or one of the tram tours that goes in there, that is not a mock-up or like a recreation. I mean, it's sort of a recreation, but like the physical space is the same physical space, and the consoles are in many cases the same consoles that were used for all of the Apollo flights. For Apollo, the MOCR was arranged in a theater-style layout with 4 tiers of consoles facing these 5 large upfront displays. And this photograph, by the way, I took this just a few months ago. This is the restored mission control room that you can see if you go on a tour. And it is dressed with all of those like ashtrays and papers and everything. This, you can see there's folks in the front of the room. I shot this like while they were still finishing everything up. This is a week or so before it opened, but it looks, right now it looks incredible. It looks more or less exactly like it looked in the 60s when they were actually running the missions. So there are 2 chunks of consoles. This is a diagram of the layout of mission control. So the photo that we just saw, let me go back. The photo here that we just saw, this is standing right next to the desk right in front of me there. To the left is the flight controller's desk, or I'm sorry, the flight director's desk, which is the number 5 desk on there. So I'm standing in that photo right behind the number 5 desk. So when you break these consoles down, there's 2 chunks of them that are particularly important. The front row outlined in green, and that second row to the right outlined in red. The front row outlined in green was called the trench, and it was called that for various reasons. There's a bunch of competing stories about why the front row was called the trench. But the trench was, those were the trajectory guys. They were concerned with the launch, guidance, and return of the Apollo spacecraft and the booster. The red consoles on that right part of the second row are the systems guys. The systems guys' collective role is to monitor all of the things that are going on with both the command and service module and the lunar module, all the things that the astronauts didn't have time or ability to monitor. And that was most of the spacecraft systems. A couple of other important positions on mission control, the one number 12 there, that's the CAPCOM or capsule communicator position. CAPCOM is the only person nominally allowed to speak to the astronauts. The idea there being that you only want one person talking to the spacecraft so that everything is relayed to that one person and nobody gets conflicting instructions when they're on orbit or going to the moon. And then position 5, which I mentioned, was the flight director who oversees the entire mission. The other positions there are support positions like surgeon and recovery. And then the back row in purple, that's consoles number 1, 2, and 3, were reserved for high up NASA management and the Department of Defense representative who would be there. So the primary role of mission control during a mission, essentially, is to keep track of stuff. They keep track of where the spacecraft was and where it was going. They keep a constantly updated set of instructions ready to go in case the mission needs to be aborted at any moment. They keep track of where the mission is on the timeline, because every minute of these things is planned out. What activities are coming up, whether something's taking too long, and most importantly, the health of the spacecraft itself, because the Apollo spacecraft is the most complex vehicle ever designed by humans up to that point, and the lunar module was sort of a close second. And there's so much going on that even with this is a image of the, or a diagram of the Apollo command module console. This is like when you're in the spacecraft, this is the panel that you're looking at. And you can, if you guys want to look a little closer at this, you can find, I pulled this off of a website called herorelics.org, HERORELICX.org. They've got tons of this stuff up there. But in spite of how complicated this control panel is, there's not a lot of stuff on it. There are a lot of spacecraft systems are simply not exposed to the astronauts. The decision was made early on to chop up the workload between what the astronauts do and what mission control does. The astronauts focus on astronaut tasks. They fly, rendezvous, dock, land, and run experiments. They have some amount of control over the environmental systems and the comm systems, and they can do all their own guidance and navigation independently if they need to, in case there was a communications failure. But their primary job is flying the spacecraft, not really watching over the health of the spacecraft. The health of the spacecraft is watched over from the ground. The reason why there's all these mission control consoles, and each controller also has a dedicated backroom staff of 3 or 4 or 5 more people who watch the things that that controller can't watch. That's just, I mean, it's just how complicated these systems were. And that's how limited the automated methods of monitoring things were in, in the early 60s when all of these systems were being drawn up. So you've got the watchers in the red console, and then you have, let's see, on this red section here, consoles 13 and 14 are ECOM and GNC. ECOM is electrical, environmental, and communications. GNC is guidance, navigation, and control. These two guys, 13 and 14, watched over the command module. And then you've got 15 and 16. 15 is TELMU, which Gene Kranz notoriously mispronounced constantly as telemu. If you hear him on all the tapes, that's what he says. TELMU stands for Telemetry, Electrical, and EVA Mobility Unit. I had to look that one up. TELMU is to the lunar module what ECOM is to the command module. And then position 16 is called control. Control is to the lunar module what GNC is to the command module. ECOM is in the environmental stuff. GNC is the health of the computer. TELMU is the, I'm getting mixed up too now, is the electrical stuff on the lunar module, and then control is the computer. And then up at the front, on the trench, you've got the booster console starting at 17, and that was a big console that watched over the state of the Saturn V itself. And during launch, they'd have a rep from the Marshall Space Flight Center in Huntsville also seated there. That keeps track of after they watch over the rocket, and then what else we got here? The next two over there, the flight dynamics officer and the guidance officer, they watch what the spacecraft is, and then the retro officer computes the abort options. So it's kind of a big, heavy data dump. But so this is the first like really, really interesting bit that I found when I first did a mission control tour in 2012 behind the scenes. And I got to reading a little bit about how the displays on the consoles were generated. So what I'm talking about here is these two displays here. This is the I'd have to look and see exactly what console this is. I don't remember, but the two displays here, and then the one that I included on this slide here down at lower right, are not single generated rastered images like you'd get on a modern computer. They are, okay. The way that your displays worked when you're sitting at mission control, controllers select what they want on their screens by selecting a channel, like exactly like changing the channel on a TV. And each page of information that a controller might want to look at is assigned to a TV channel, basically. And there's a list at the beginning of the mission during launch. There's a list of the available TV channels, and they put it in the big up front display, and you can configure your console to make sure you've got the right channel up on your screens there. Like if you need the, what is this, the lunar descent and ascent digitals, that's from channel number 84. So you put your device on channel 84, and this is the screen you'd see. And if your buddy needed to see the lunar ascent, descent and ascent digitals, he'd turn to the same channel and could see the same data. Let's see. Oh, and then this little bit where it says TV channel 16 up in the corner there, that's the, it's mismatched with this. This is a photo from the recreated mission control, but that's the number of the TV channel that you are currently tuned to. So actually generating these images is, oh wait, I have one more thing written here. So every position has what's called the display request keyboard. That's the thing at lower left with all the blank black buttons on it. During the mission, those would have labels on them. And then a manual select keyboard, that's the thing at upper left with the dials on it. So your display request keyboard is pre-programmed with all your screens you need. So you'd have labels on every one of these, and rather than having to manually change to a specific channel, you would just press the one that you'd want to go, and it would flip to that channel for you. In every station, every console would have its own set of channels pre-configured. If you needed to look at a channel that wasn't pre-configured, you'd use that manual thingy up in the upper left. You fiddle with those analog dials and hit the go button, and that's how you select a channel that's not pre-programmed in your list. So this is the best part. So the displays themselves, they're not rasterized images. On the first floor of the Mission Control Center was a room with dozens and dozens of CRT screens. And those screens were connected back to one of the big IBM System 360 mainframes that were running the mission. And each of those CRTs, each of those screens in this first floor room displayed the raw numbers that were used for that particular information channel. So I don't remember what the total number of channels available was. It was 50 or 60. So there's 50 or 60 of these screens. And each of these screens, which just have like bare numbers on them, have a camera pointed at it, filming the screen. And then nearby is this enormous bank of slides, like Polaroid type slides, like little, slides. And the slides have the non-numeric written portions, the static portions of those displays written on it. So column headers, the solid lines for separating columns, the individual like unchanging, anything on the display that didn't change essentially was inscribed on a slide. Maps, graphical elements, any of that, anything that's not a dynamic number that changes. And the slides are projected via this system of lenses into the cameras pointing at the screens. And so what the controllers are looking at is literally an optical composite of like a camera pointing at a screen with a slide in front of it to show all of the column headings and numbers and everything. And the actual changing numbers were just flickering on the CRT downstairs. It was like, it's the most like Rube Goldbergian system. And every time you needed to draw up a different display, there would be this mechanical slide changing that would happen, and like the right slide would get dropped in and projected. It was absolutely ridiculous. But again, this is 1964, 1965, and this is what you do. You don't have character generators like you'd have at a TV station or anything modern. You have to make this stuff. It's absolutely crazy. The upfront displays had their own systems that were just as ridiculous. All of this is outlined in and available to read on some of NASA's manuals they have online. It's great stuff. So, okay, we're going to talk a little bit about how mission control adapted to a couple of serious spacecraft problems that happened. And we're about to hit our first video clip. So the key to mission control for all of these things is intensive training. These guys spent, as you know, hundreds and hundreds of hours before every mission simulating all aspects of it, trying to figure out, what could possibly go wrong. And the only thing that was off limits during simulations like this was the simulation supervisors weren't allowed to purposefully kill the astronauts. Like you weren't allowed to construct a situation that had no out. Because it was determined there's really no value in negative training. You never want to like train your astronauts to think like, well, okay, I guess I tried everything, so we're just going to die now. Every training had a solution to it, and this all kind of paid off several times. But one of the most famous ones was during the launch of Apollo 12, when the way that the day was saved is like so very, very impressive. So we've got a YouTube link here. And let me see, whoops, let's go back here. I may have to stop presenting for a second. Actually, you know what? Let me stop screen share, and I'm going to, my web browser go, there it is. So I'm going to drop this in the chat. I'm going to send it to, let's see, can I send it to everybody? Yes, I can. All right, here we go. So folks, if you'd like to, click on the YouTube link that went up in the chat. You may have to press the chat button on there. I'm not sure how your clients look, but I just dropped it in there. Now, this video is a clip from the HBO miniseries From the Earth to the Moon. It shows the launch of Apollo 12. This is a pretty faithful recreation. A lot of the dialogue here is taken directly from the air-to-ground transcript. This video is 3 minutes and 55 seconds long. So we are going to pause here while everybody queues it up and hits play, and then I will watch it on my screen here, and then when it is over, we'll resume talking and we'll talk about what happened. So if everybody sees it, you may have to pull your chat up so you can see it, but click on the link, and we will be back here in about 4 minutes.
Sure. LB, you are going on the moon. Y'all come along if you like. 10, 9, ignition sequence started. The engines are on. 3, 2, 0. First few minutes after liftoff, you're vibrating pretty good. Clock is running. Then you really start to move. You got just over half a minute of 23 moments, and then all hell was to use. AC bus light, fuel cell disconnect, AC bus overload 1 and 2, main bus A and B out. We had some big glitch here, gang. I got AC. Got AC? Yes. There's just the indicator. Wake up the main bus. 24 volts. That's low. We got a short on it at some time, but I can't believe that's accurate. Flight Ecom. Go Ecom. I think it's a fuel cell bus failure. They've been thrown offline somehow. Must be why we're getting garbage here. Can they try SCE to AUX? Jared Griffin had never heard that command before. I'm pretty sure most of the people mission control have. Hello? Apollo 12, Houston. Try SCE to auxiliary. Over. SCE to auxiliary? What the hell is that? CE. I'm not sure even Pete knew what that was. But one person did. I know what that is. SCE to AUX. We get good telemetry from the Try to reset your fuel cells. Reset fuel cells. Wait for staging. Wait for staging, yes. Hang on. Okay, Mr. GC, it's good. We got a good S2 gang. Copy that, Pete. You're looking good. Poor Jerry Griffin. We were his first mission as flight director, and well, he had dealt with a longer list of malfunctions than anybody had ever seen. Okay, now we'll straighten out our problems here. I don't know what happened. I'm not sure we didn't get hit by lightning. That's exactly what had happened. Before even our first stage had finished doing its job, observers back on the ground later reported that not just one, 2 bolts of lightning rode our exhaust contrail all the way back down to the pad and hit the tower. That was a hell of a simulation you guys gave us. I think we got to put this through a little more all-weather testing, guys. Okay, Al's got all the passing craft online, and we'll just square up our platform when we get into orbit. So, I've done my part to help out in the crisis. Of course, that econ fellow, John Aaron, well, we owe a lot to him. But to me, the real hero was Pete Conrad. He kept his hand on the abort handle the entire time. He kept his cool, and he never used it.
Wow. Okay, let me reshare. Wow. And let me do the full screen thingy. Okay, so folks who are coming back here, we're going to continue on. So this clip's a pretty faithful recreation of the near disaster that happened during the launch of Apollo 12. The dialogue on the air-to-ground dialogue is almost verbatim, though John Aaron's a little talkier here than he was in the real event. So what the hell happened? So the spacecraft was literally struck by lightning during launch. This was still one of the early Apollo crewed launches. It was, at the time, they didn't have some of the weather rules that they have now. In fact, some of the weather rules that they have now are because of Apollo 12. So the spacecraft was hit twice by lightning, and the strike tripped breakers on the spacecraft and disconnected a lot of systems from the spacecraft's main electrical buses. The fix was to set SCE to aux. But what does that mean? So SCE, the SCE is the signal conditioning equipment. It's like a black box in the command module. It's part of the communication suite that translates the raw electrical sense voltages from the equipment on board the spacecraft into a format that can be read by the ground. So it takes all the different varying voltages of all the different gauges and sensors on the craft, and then translates them and normalizes them for the ground. The lightning strike, in addition to disconnecting a lot of stuff, screwed up the SCE and dropped power to it, which caused the telemetry feeds to look like garbage on the ground. Switching the SCE to the auxiliary, the SCE switch to the auxiliary position puts the SCE in a low power mode, which enables it to run on reduced power. So once that was done, the MOCR was able to see what the telemetry feeds were and advise the spacecraft on what to do next. So John Aaron, the ECOM controller who made that call, was by everyone that I've spoken to, and John Aaron is one of the few Apollo guys I haven't had a chance to interview yet. He was like Superman. He was the smartest guy in the room, or at least he was the smartest guy who ever sat at the ECOM console. To hear the tale told by Cy Liebergott, one of his contemporaries, who also worked as an ECOM and who worked on Apollo 13, Aaron's ability to recall little tiny wiring and circuit diagrams was absolutely unparalleled. When Apollo 12's telemetry went offline at the lightning strike, so what you saw on the screen, the most over dramatized part of that is that when it happened, John Aaron didn't say anything. He sat there and stared in dead silence at his screen for about 10 seconds and then just announces the fix over the loop. He just says, have flight have them set SCE to auxiliary. And he later said, when he was asked about it, that the reason why he was able to come up with the fix was because he recognized the pattern of garbage data on the screen. Like, he recognized the characters and the way that the garbage data was arranged from an exercise that was simulated a few months prior, where a low voltage condition was one of the issues that they were thrown. He was able to mentally look that information up in about 10 seconds during a launch, where if they hadn't been able to reestablish that telemetry, it would have had to be an abort. They would have had to throw the mission away, and possibly people could have died. And his quick thinking instantly saved the mission. And it's not really even, if you're a spaceflight insider, you know about it, but it's not like a broadly discussed public thing. It's nowhere near as broadly discussed as like Apollo 13, for example. But that was the quality of person who sat at those consoles. And this is a great opportunity to segue into talking about absolutely my favorite subject in the entire world, the Saturn V rocket. Every component of Apollo was critical to the success of the program, but it doesn't get much more critical than the rocket itself, because without the Saturn V, we never would have gotten to the moon. So the Saturn V is a 3-stage rocket, and each stage has a different function. The first stage's job with those big, gigantic F1 engines was to power the rocket up out of the low, dense, thick part of the atmosphere. The second stage's job with its liquid hydrogen engines was to provide the majority of the speed, the delta V, necessary to get into orbit. And then the third stage was a multi-purpose stage. The third stage had to give them their last little kick to get into orbit, and also had to push them out of orbit in their translunar injection maneuver to fly to the moon. This is an exploded view of the rocket looking down forward. And just very briefly, at the very bottom, you've got the S1C, the first stage. The designation for the first stage is the S1C. There's a little ring, the interstage. And by the way, if you guys have seen, there's an incredibly famous spaceflight video clip. I'm sure you've seen it. It's like the back view of a rocket, and you're looking, and like this ring-shaped thing falls away and twists. And what you're looking at is the first stage interstage of the Apollo. I think it's the Apollo 4 uncrewed test flight falling away. They rigged that rocket up with dozens of film cameras, and it captured that, incredibly cool. That's the interstage dropping off. Next to that, you have the S2, the second stage. There is a conical interstage on top of the S2. That's that black and white checkerboard looking doodad. The next thing up is the S4B. That's the third stage. On top of the S4B is the IU, the instrumentation unit. That's that little black ring on top of the third stage. That's where the rocket's computers are. Next, you have the SLAW, the Spacecraft Lunar Module Adapter, with its panels opened. That's the area where the lunar module was nestled at launch. And then on top of that is the lunar module, then the service module, the command module. Then on top of the command module is the white boost protective cover, the BPC, and the LES, the launch escape system. The Saturn V was the magnum opus of this gentleman, Wernher von Braun, the foremost rocket scientist of NASA in the beginning, and also the foremost rocket scientist of Hitler's Reich. And I say that not to be inflammatory, but because it's impossible really to put von Braun in context without acknowledging that he was a member of the Nazi Party, likely out of necessity in order to be able to hold the position of power he had over rocket design. And there's a ton of this to read. I'm not going to go into any of it, but von Braun is a fascinating man. He had dreamed since he was super duper young of flying rockets to the moon and to Mars, and grew up and decided to do that. He had designed Germany's V1 and V2 rockets, which is obviously not a good thing, but the reality is the design of those rockets helped to pave the way for the design of the Saturn. He was smuggled out of Germany at the end of World War II in a joint CIA-OSS operation called Operation Paperclip. There should be a movie made about it. It is fascinating. Totally read it. It's amazing. And sent to live in Huntsville with his team, working on first military applications for the Army at the Redstone Arsenal, and then later on spaceflight concepts, first for the Air Force and then for NASA. Freed from having to make war machines, he and his team of expatriated German rocket scientists designed the Saturn series of rockets for NASA. with typical Teutonic engineering conservatism, the design for the Saturn was massively over-engineered, especially the first stage, to the point that after the first few flights, when NASA wanted to begin to augment the surface capabilities of the Apollo spacecraft, especially the J missions at the end where they had the lunar rover and everything, they were able to come up with the additional power to do that by taking the safety margins of the Saturn V from ridiculous to a lot. They were able to build in a considerable amount of additional payload capacity just by deleting some extra safety stuff that had never even been come close to being used. There were also, one of the other key things that von Braun did was that Apollo 12 lightning strike that knocked the command module's guidance system out. The Saturn was designed with its own independent guidance system. The idea being that maybe we would want to use this rocket instead of carrying spacecraft to someday carry cargo. If the Saturn hadn't been designed with its own independent guidance, that lightning strike that knocked out the guidance platform on the spacecraft in Apollo 12 the rocket would have probably begun to tumble. The vehicle would have broken up, and if everybody would have died, it would have been catastrophe. There is a great joke in this book, by the way, right here, this Apollo, The Race to the Moon by Cox and Murray. You absolutely should buy this book. This is the only book that every Apollo person I've ever interviewed said that this book gets it right. There's a great joke in there, and I'm going to quote, I wrote it down here, so quoting Cox and Murray, quote, "The joke that made the rounds of NASA was that the Saturn V had a reliability rating of 0.999. That's a 4.9 reliability rating. Folks who have done any engineering, you know what that means. That's good. That's a good reliability rating. In the story, a group from NASA headquarters travels down to Marshall and asks Werner von Braun how reliable the Saturn is going to be. So von Braun turns to four of his lieutenants and asks, "Is there any reason why this won't work?" To which they answer, 9999. Von Braun then says to the men from headquarters, "Gentlemen, I have a reliability of 4 nines." That's the joke. Okay. The coolest thing about the Saturn V, in my opinion, is this. This is the F1 engine that powers the first stage. This is the largest single-chambered liquid-fueled engine ever successfully built and fired by humans. And frankly, it will almost certainly go down in history as being the largest one we ever built. If we were going to do this again today, we wouldn't do it with a single giant or with 5 gigantic engines. To give you an idea of scale, if you've never been down to JSC to see these, in that photograph at the lower right is my wife, and she's about 5'4". So that's how big that rocket is. And the first stage used 5 of these things. 20 feet tall, 12 feet wide. The specs on these engines are absolutely, they're just beyond belief. Each one of these things put out 1.5 million pounds of thrust and burned 1 ton of RP1, that's kerosene, an aviation grade kerosene, and 2 tons of LOX per second. And that's one engine. And the first stage had 5 of them. So every second the first stage is lit, it's flinging 15 tons of propellant out the back of the thing. The F1 is what is called a gas generator cycle engine. If you guys are familiar at all with the different types of rockets, a gas generator engine is one of the simpler rocket types. It's much, much simpler than like a staged combustion engine like you find on the space shuttle. If the space shuttle engine is a Ferrari, and it really, really is, the F1 here is more like a Mack truck. A gas generator type of engine simply means that the engine uses a thing called a gas generator, which is a smaller rocket engine located above the thrust chamber to turn the pumps that draw fuel and oxidizer out of the tank and into the thrust chamber. Think of blowing on a pinwheel, basically, to make the pinwheel spin. Except instead of blowing on a pinwheel, it's rocket exhaust turning a turbine. The gas generator exhaust spins the turbine, which drives the pumps. The gas generator in an F1 is so powerful that by itself, it puts out more thrust than an F-16 at full afterburner. And again, that's just to turn the pumps to get the juice into the real part of the engine to do the real work. This is a photo I took in 2012 at Marshall of an F1 gas generator that had been pulled from an old F1 engine in storage and hooked up and fired. This was taken with a very long lens. I'm actually very, very far away from this when we took the photo. The purpose of this was actually to do some testing on the old F1s and find out some of their operational parameters, because a lot of the fine points of F1 operation and design aren't really known as well as they were. We still have all the blueprints and everything, but there's a lot to learn about how those old engines worked, because we didn't have the benefit of computer modeling and simulation. We don't know a lot about their edge case parameters and blah blah blah. I don't want to get off topic here, but anyway, so an F1 gas generator, when it fires, looks like this. That's a photo of one. So you have to imagine that thrust then being channeled into a turbo pump and spinning the pump to actually like suck the fuel out. All of that power is used not just to pump the fuel into a thrust chamber, it's used to jam the fuel through this 44-inch wide plate, the injector plate, which is a big flat copper and steel sandwich with concentric rings of holes drilled in it. And each ring of holes injects either RP1, the kerosene fuel, or LOX, the liquid oxygen, the oxidizer. And they spray in these very precisely aimed atomized streams so that everything is like perfectly, burned. That's kind of the most remarkable thing about this. It's not that the engine moves 3 tons of propellant per second. It's that it takes 3 tons of propellant per second and squeezes them through these tiny little holes. I mean, tiny, 44 inches is pretty big. This is not like a tiny plate. It's large, but it ain't that large. It's not. It's small enough to where it's like they put how much through that every second. Really interesting thing. Okay, so these baffles, these raised copper baffles on the surface of the plate, they are not just for decoration. They serve a very important purpose. They literally stop the engine from exploding. During its development, the F1 suffered from a problem pretty common in rocket engines called combustion instability. It happens, but the fact that the F1 was so much larger than any contemporary engine meant that solving the combustion instability problem was considerably harder than with a smaller rocket. Again, this was and remains the biggest single-chambered liquid-fueled engines that we've ever made. So what combustion instability is, as the plume of the rocket's exhaust is burning inside the thrust chamber, it oscillates thousands of times per second. Because it's just the sort of the nature of the fluid dynamics of it. The propellant is injected, it burns, and as it burns, the plume spins many, many thousands of times per second. And with the F1, sometimes that oscillation had a tendency to go from smooth to wobbling very quickly. And that's a lot of mass. Remember, we're talking about at any given moment in that chamber, you've got 3 tons of propellant being pumped in there, and that's a lot of speed, and that's a lot of momentum. And when you've got 3 tons of propellant wobbling, what happens is the engine explodes. It just explodes. And they couldn't figure out why, and they couldn't figure out how to stop it. So the solution was to stop these things from blowing up on the test stands. Today, what we would do is we'd build a computer model of it. We'd put it in MathCAD or Wolfram or something. We'd simulate it. We'd find out what the problem is, and then we'd build the real one without the problem in it, because we can do that now. You couldn't do that in 1963, 64, 65, all the time that this engine was in development. So they had to start taking guesses at how to damp down its instability. So they started putting baffles on the injector plate, building a model, firing it, watching it blow up, and then changing it slightly, building a model, firing it, watching it blow up, changing it. And so they iterated through this design until they arrived at this particular arrangement of baffles. 1, 2, 3, 4, 5, however many on the outside and 4 on the inside. That is, this turned out to be the arrangement of baffles that stopped the engine from exploding. And they got to the point where they would try to induce instability by jamming a large charge of black powder up into the combustion chamber while the engine was firing and setting it off, basically setting a bomb off inside the engine to try to induce it to wobble. And with this final baffle arrangement, the engine would actually self-stabilize even with a bomb going off inside of it within about a second. The really fascinating thing is nobody's really sure if this is the optimal arrangement or not. What we know is this is the arrangement that was good enough to where it would stay stable for far longer than the actual firing time of the engine during a mission. Because these things are only used for about 150 seconds. That's how long about the first stage of a Saturn V burns. 2.5 minutes and then you're done. So it only had to stay stable for 2.5 minutes, and this is the arrangement that did it. There wasn't any more time to work on it either. At that point, it had been several years. Like, it took years to get to this point. This is not just like they did this in a week and we're like, okay, great. This is like years of building and blowing these things up. Okay, so before we leave the F1 engine, I hope that this might actually answer a question, because this answered a question of mine when I figured this out, and from reading all this stuff. The exhaust from this gas generator, you got to do something with it. Like, it's sitting up here on top of the engine, turning these turbines, but you have to do something with this exhaust because, excuse me, it's not an inconsiderable amount of exhaust. So the way this works is, after the gas generator's exhaust turns the turbine, after it passes through the turbine and out the other side of the turbine and has done its propulsive work, the exhaust is vented down this manifold that you can see. I guess, I don't know if my mouse cursor is, whoops, nope, go back, we're not done yet. I don't have a cursor that I can point with, but so on the left picture, you see the engine bell, and there's sort of like this thing coming down next to the engine bell and wrapping around it like two fingers. That's the gas generator exhaust manifold. So the gas generator exhaust is vented down this manifold and then is dumped through vents in the inside of the nozzle into the lower half of the nozzle, where it coats the inside of the nozzle. And it's at about 1200 degrees Fahrenheit. The exhaust inside the combustion chamber is like at 4,000 or 5,000 degrees Fahrenheit. So the exhaust from the gas generator actually provides a thermal curtain that insulates the bottom half of the engine bell from the exhaust of the actual engine. The gas generator exhaust is very fuel rich, so it takes considerably longer to combust than the already burning optimal mixture up in the upper part of the engine. And so it then vents in this dark laminar flow, like area of flow below the engine before it ends up igniting. And that creates what I had always wondered, like, why does the exhaust of an F1 look like this? Why do all the launch pictures of an F1 engine show this, dark thing coming out of the engine before the big exhaust plume happens? Well, that dark bit coming out of the bottom of the engine is the vented gas generator exhaust that takes a little longer to combust than the fuel in the actual engine. So that's what that is. You're looking at the gas generator exhaust after having done its job of protecting the bottom part of the engine nozzle, venting out below and then combusting and sort of expanding. So now you know. We are at, let's see, how are we doing? We've got a few slides left here. We're going to talk a little about the Apollo guidance computer, which is another one of my favorite topics. We're going to hit a couple of neat things about it. So you've probably heard the old bit about how, we flew to the moon on less power than a pocket calculator. We flew to the moon on less power than a digital watch, That's kind of true. But it's also a gross mischaracterization of what computing power means in different contexts. Don't think of the Apollo guidance computer as a modern computer. Think of it as a very sophisticated, very powerful, purpose-built embedded controller hooked up to and designed around the peripherals that it had to control. Now, I say peripherals in 2020, and you think like printers and scanners and stuff like that. But peripherals in 1960s Apollo terms are things like the steerable radar antenna, the throttleable, ascent or the throttleable descent engine in the lunar module, the communications stuff, like all of the spacecraft systems were the computer's peripherals. It's one thing to design a computer that can go to the moon. It's another thing to do it in 1960 and at the same time invent the entire field of real-time computing and think of ways to solve problems that become the textbook ways to solve those problems in computer science from then on. That's what these guys did. They didn't just, make a little crappy computer that like does math slower than a watch. It's really hard to blow it out of proportion. It's hard to like over exaggerate the complexity of the design work that they had to do. And the fact that a lot of it was done by, especially the programming aspect of it was done by college students who didn't have grounding in dogma of modern computer design because there was no such thing. It was folks like Don Iles who helped us go to the moon. Don Iles, by the way, has an excellent book that you should buy. It's called Sunburst and Luminary, talking about his time doing this. And what I learned from that, I learned a lot of stuff from that book. One of the things I learned is that going to the moon, the software that got us there was the result of a lot of pot. Like there was a lot of that going on at MIT in the 60s. But apparently it worked because we did in fact get there. The Apollo guidance computer hardware was all based around core rope memory. Some of you folks who are older, who have been around computers for a long, long time, probably have some, basic familiarity. Even if you never used a core rope computer, you probably have some basic familiarity with the technology. Very, very, very briefly, it is a way of encoding data, encoding software, basically, by you take a magnetic ring and you thread wires through it, and the way the magnets go tell it whether it's a 1 or a 0, and you have various amounts of bits that are stored in the physical intersections of hardware. This is a cutaway view of a module that would go in an Apollo guidance computer. This is a ground version or an unflown test version because it's not, because you can see what's going on. In the flight versions and in most of the later test versions, all of the airspace in here was filled up with an epoxy potting compound, which gave the modules extreme resistance to G-shock, radiation.
Al Bean, you are going to the moon. Y'all can come along if you like.
13, 12, 11, 10, 9. We have ignition sequence start. The engines are on. 4, 3, 2, 1, 0.
The first few moments after liftoff, you're vibrating pretty good.
Clock is running.
But then, you really start to move.
Clear the tower.
Roger, clear the tower. I got a pitch and roll program, and this baby is really going. Roll complete.
Mark 1 Bravo.
Got you on that. This thing moves, doesn't it? Yeah, baby.
We had just over half a minute of trouble-free launch, and then all hell busted loose.
I just lost a whole bunch of stuff. Roger, we just had a whole bunch of buses drop out. What we got here, AC bus 1 light, all the fuel cells. Okay, Houston, we just lost the platform here, gang. I don't know what happened here. We had everything in the world drop out. I got 3 fuel cell lights, an AC bus light, a fuel cell disconnect, AC bus overload 1 and 2, main bus A and B out. We had some big glitch here, gang. I got AC. Got AC? Yes. Maybe it's just the indicator. What do you got on the main bus? 24 volts. That's low. We got a short on it of some kind, but I can't believe that's accurate.
Flight Ecom.
Go, Ecom.
I think it's a fuel cell bus failure. They've been thrown offline somehow. That must be why we're getting garbage here. Can they try SCE to aux?
Jared Griffin had never heard that command before. I'm pretty sure most of the people in Mission Control hadn't.
Tell him.
Apollo 12, Houston. Try SCE to auxiliary. Over.
FCE to auxiliary. What the hell is that?
CE.
I'm not sure even Pete knew what that was. But one person did.
I know what that is. SCE to aux.
We're getting good telemetry from you again. Try to reset your fuel cells.
Reset fuel cells. Wait for staging. Wait for staging, yes. Hang on. Okay, Houston, GDC is good. We got a good S2, gang.
We copy that, Pete. You're looking good.
Poor Jerry Griffin. We were his first mission as flight director, and, well, he had dealt with a longer list of malfunctions than anybody had ever seen.
Okay, now we'll straighten out our problems here. I don't know what happened. I'm not sure we didn't get hit by lightning.
That's exactly what had happened. Before even our first stage had finished doing its job, observers back on the ground later reported that not just one, but 2 bolts of lightning rode our exhaust contrail all the way back down to the pad and hit the tower.
That was a hell of a simulation you guys gave us. I think we got to put this through a little more all-weather testing, guys. Okay, Al's got all the buses back online, and we'll just square up our platform when we get into orbit.
So, I'd done my part to help out in a crisis. Of course, that Ecom fella, John Aaron, well, we owe a lot to him. But to me, the real hero was Pete Conrad. He kept his hand on the abort handle the entire time, but he kept his cool, and he never used it.
Anything involving physical forces. So they would, not only did they do this and build it out of very resilient stuff, they also filled every bit of empty space inside of it with epoxy so it couldn't, shake around. The specs on the computer, I won't dwell on these. If you know computers, this is very, very primitive sounding. this is just not a lot of capacity. But specs don't tell the entire tale for this, because it's not so much that this computer doesn't have a lot of power. It's that this computer has the amount of power that it was required to have to do the job, which also happened to be like, you know, the bleeding state of the art in the mid to late 1960s. From a software perspective, it was pretty sophisticated. It had a real-time operating system called the Executive. It's not really an operating system, but we're going to call it an operating system because otherwise we'd be here talking terminology all day. That effectively operated in sort of a batch scheduling mode using a very, very primitive form of co-op multitasking. It also had a very sophisticated, you'd call it an interpreter, and it was named the interpreter, that functioned almost like a primitive virtual machine. And it enabled the guidance computer to do a lot of the guidance math that it had to do with complex math, even though it didn't have the hardware to do that. It actually emulated a more complex computer sort of in software, and then did all of the complex floating point math in software, even though it didn't have the hardware to do it, which is really cool. None of this sounds outlandish in 2020. I mean, this is basic stuff. But again, you have to remember, these folks are making this up as they go along. They're inventing the entire concept of a real-time operating system without Google, without textbooks, without existing best practice guidelines. They're creating the best practice guidelines as they go along. I mean, it's all well and good to emulate or to implement emulation that can do in software stuff you can't do in hardware today. It's an entirely other thing to invent the concept of doing that in the 60s. This is just amazing stuff. How well did it work? Well, it worked well enough to save the Apollo 11 landing when things went horribly, horribly wrong with the computer alarms that we're going to talk about here. So setting the stage very quickly. This is a quick diagram, by the way, of how you land on the moon. There's no air, so you cannot use wings, parachutes, airfoils, nothing like that. You have to use rockets to land on the moon. You have to. This is why the Apollo landing process was called the powered descent process. They had to ride their own rockets thrust down from orbit to the surface. Powered descent was a very complex and involved procedure, and it was endlessly simulated by controllers and astronauts. And there were a ton of moving parts to powered descent. And if anything went wrong, the only way out of it, once you're kind of committed to landing, was to abort the landing. Well, that doesn't sound too complicated, but aborting the landing means you smack the abort button, the lunar module blows itself in half, you drop your descent stage, the ascent engine fires, and you have to go and like lift yourself up out of your downward trajectory and go and find your command module. It is what engineers would call a very dynamic process, since you're blowing your spacecraft in half and doing all kinds of crazy stuff. Powered descent is about the worst possible time for anything to go wrong during a landing. That's the phase where you're most busy. And so, of course, for the very, very first lunar landing, that's exactly when everything went like totally wrong. So we have another video clip here, and the second video clip is from the movie First Man, and it is a little over dramatized, but it also is I think it's a very faithful tone and feeling recreation of as these guys were landing, watching these alarms go off. And it does very accurately show how quickly they dealt with the problem and pushed on to finish the mission. Okay, so this clip is 5 minutes long. I don't want us to watch the whole thing. My request is that we watch the first 90 seconds, which is really the only part we care about. Although if you'd like later, please feel free to watch the whole thing. Feel free to watch the movie. It's a fabulous movie. Robert Perlman, a friend of mine who runs Collect Space, he was involved in consulting with the movie. And First Man gets things very, very right. Okay, so just like we did a second ago, I'm going to stop sharing, and I'm going to paste this YouTube clip into the chat. 1 second. Let me find it here. Let me paste it down here. Okay, so again, please just watch the first 90 seconds. Don't watch the whole thing, even though it is awesome. Just kill it at 90 seconds and then come back.
Give us a reading on the 1202 program. Roger, we got it. We're drawing that alarm.
Whoop, there we go. Now I'm not muted anymore. To find where put my bar on which screen here. Okay, so we should all be back now. That is a seriously, this movie is so damn good. The filmmakers demonstrate a tremendous respect for the source material and also an almost uncanny attention to detail and accuracy. There's some dramatic liberties taken to make it more watchable because when space flight goes right, it's super duper boring, frankly. But the movie succeeds just brilliantly in giving audiences a realistic look at not just the technology that got us to the moon, but the people who flew there. The quiet scenes with Armstrong and his wife are very, very good too. Anyway, if you haven't seen the movie, please go see it. It's totally awesome. So let's talk about what the hell just happened, because that was sort of a lot of things were going on there. But the essence of it was, they're trying to land and you got these 1201, 1202 alarms going off. What does that mean? So the 1201 and 1202 alarms are what are called executive overflow alarms. And this may get a little technical because this is one of those things where it seems like it's easy to understand, and then you dig into the root cause of what exactly is going on, and it's like stupid complicated. So I've tried to boil this down to high level. But if you want to know more about exactly what this is, Don Iles, the gentleman I mentioned a minute ago, not only does he describe it in his book, he's got a site here that it's in the presenter notes, and I can paste it into the chat, where he goes into a much, much more detailed root cause analysis of what happened. Basically, they're trying to land, you get these alarms. These are executive overflow alarms. These are alarms that warn that the guidance computer has run out of temporary space, basically space to store variables and things that it's working on. And this should never happen. These 1201, these 1200 series alarms are debug alarms. They were in there because they were used when the code was being written, but they were not alarms that were supposed to be able to happen during a mission, because the program flow was very carefully controlled. When they wrote the software for this, it wasn't like writing Microsoft Windows, right? Like, they knew exactly how it was going to be used, and they knew exactly how many resources were going to be available, and the programs were all written to fit in the available resources. Running out of temporary storage space is not something that is supposed to be able to happen. When you read about this, you commonly hear this chalked up to a checklist error. In fact, even Margaret Hamilton, who ran the MIT instrumentation lab, has said that this is a checklist error. Now, I have to say that Margaret Hamilton knows a hell of a lot more about Apollo than I do. But in this specific area, it's not real. This was not actually a checklist error. This was a design documentation error that led to the checklist saying a thing that the checklist shouldn't have said without the design error being corrected. Basically, what happened is they're coming into land. And before they land, Buzz Aldrin, standing in the lunar module pilot station on the right side of the limb, activates the rendezvous radar. And he activates the rendezvous radar as they're about to land, not because they're supposed to rendezvous with everything, but because if they have to abort, if something goes wrong during the landing, the rendezvous radar is how they're going to find the command module. And the idea was, we'll turn it on now so that if everything goes sideways, this is what we don't have to worry about turning it on then, it's already on. So the rendezvous radar was energized and put in the slew mode, which controls which axes the radar antenna was steerable on by the computer versus manually steerable, I think. So he flips this switch on. Okay, so here's where we get a little complicated. The guidance computer, the lunar module's guidance computer, is hooked up to the radar by a thing called the ATCA, the Attitude Translation and Control Assembly. The guidance computer is able to steer the radar by using this ATCA thing. And then the radar is connected to two other devices called the coupling data units that feed the radar's position to the computer. And if we were doing this today, there'd probably be a single transducer or something, but back then there's the computer, it sends commands to the radar through the ATCA, and it reads the radar's position from the CDUs. So just think of radar up here, computer down here, and these two doodads. Both of these doodads here, the ATCA and the CDUs, were supposed to be fed an identical electrical signal. They were supposed to both be fed an 800 hertz, 28 volt AC signal, and that's what they use for power. And they also use that signal to synchronize with each other so that they knew where the other one was and what the other one was doing, and the other signals made sense. They were modulated by that, by those two 800 hertz, 28 volt AC synchronizing currents. They're supposed to be frequency locked and phase synchronized. Due to a design documentation oversight, the system was built without enforced electrical phase synchronization. So what the practical upshot of that means that rather than both of those devices getting an identical electrical signal, depending upon when the switch was flipped to activate the radar, they might get two signals that are in phase, just because like at that exact millisecond, they were both in phase. They could get signals that are out of phase. They could get signals that are very, very out of phase. You know, there were three different phases and they all had to be aligned. When those phases are all aligned and locked, everything works. When they're not, weird stuff happens. So the out of phase condition made it so that basically the CDUs and the ATCA, essentially the Apollo guidance computer saw garbage. It did not understand what the radar antenna was pointing at, like what angle the shaft and trunnion angles were. It didn't understand anything because those two systems were being fed out of sync electricity. So the CDUs began to frantically try to fix things by sending increments of, sending these move the dish signals to the guidance computer as fast as they could be generated. Because from the CDU's perspective, the radar's broken, you got to move the dish, move the dish, move the dish. It did this a lot. It did this 12,800 times per second because it was so confused. Those 12,800 per second additional unplanned commands that the CDU is sending the guidance computer had to be handled. They had to be, viewed and understood in the computer's terms and then acted on or not acted on. Doing that, processing those interrupts isn't really the right word, but processing those interrupts sucked up about 15% of the computer's capacity. Coincidentally, at that point in the program, the computer had about 15% extra capacity. The unplanned signals ate all of the computer's headroom, basically, and made it so that the computer couldn't finish its task list that it had to get through every 960 milliseconds. So it had this job list, and it was like, we're going to do this, we're going to do this, we're going to do this, and it just basically iterated through that. And it was supposed to iterate through it every 960 milliseconds. But because all of a sudden it had more to do than it was ever supposed to have to do, it wasn't able to complete its job list within that 960 milliseconds and started sort of like if you're carrying too many things and you got to put something down so you can keep doing what you're doing, but then the place where you're putting the thing down overflows and spills onto the floor. That's more or less what was happening here. However, fascinatingly enough, the computer had a way to deal with this. And it's another one of those areas where you have to credit the designers of the systems for building these functions in without ever really understanding that they would be needed or knowing that they would be needed. And this is one of those deals where like foresight saved the mission. Even though those kinds of alarms should have been impossible, the scientists and the students at MIT who designed the software had built in the capacity for the computer to execute sort of a soft reset of itself, where it dumped all of its work but didn't erase anything and started over on its task list. And whenever that happened, it would trip one of these 1201 or 1202 alarms. The 1201 alarms, it doesn't matter. They're similar alarms. They both refer to different types of temporary storage areas. But once they were going on, the computer had to reset itself, basically. And it was able to do that without dropping what it was doing. So the engine didn't stop firing. The radar didn't stop working. The radio didn't stop. They could still talk to mission control, but it took several seconds for it to catch itself back up again. Because the overflow wasn't critical and it wasn't causing anything to explode or crash, they figured they could probably continue on with the landing, and Mission Control was able to, by doing a couple of things, figure out that the problem had to do with the rendezvous radar. How did they know? Because they really did figure this out within a very short amount of time. They knew because during a previous sim, because this always happens in a previous sim, controllers had been too quick to call an abort in response to a simulated computer problem. So the simulation supervisors, Dick Coos and some of those guys, were continually trying to come up with new and creative ways to kill their astronauts. And one of the things that they found was these debug alarms were still in the computer. So during a sim, they threw one at Mission Control, and Mission Control aborted. And that seriously pissed off Gene Kranz. He was like, what if this happens when we're landing on the moon? We're not going to abort when we're landing on the moon because of a stupid computer problem. So he grabbed Steve Bales, who was the Guido controller, and Jack Garman, who was one of Steve Bales' backroom guys, and basically said, I want you to find every alarm in that computer, and I want you to memorize every single one of them. So if any of them comes up, you know what it is. Like, memorize all of them. So they wrote this list, and this is a photograph of the actual list that they used, of all of the potential debug alarms and weird alarms they might run into during an ascent. So because of that foresight, sure enough, it happened. It happened during the very first mission that actually landed. And so when Kranz is calling out, what are we doing? Give me a reading on that program alarm. Jack Garman in the back room was able to pull up his list, find the 1200 series alarms, and realize that, okay, it's probably fine. It's fine if it doesn't recur. Give them a go. And they did. And because of his quick thinking, everybody started calling Jack Garman Gar Flash, because it was the 60s, and that's a cool 60s nickname. There is a lot more to this issue that that we could go into, but I would recommend you hit up Don Iles' website or his book and read about it, because this is just so fascinating. Okay, there was this. We're going to skip this. Whoops. So this is the very last section, and this is something that that I got into reading about a couple of years ago, and I did some interviews on it. What were the Soviets doing during this time? Because we've talked a lot about it. A lot of people know about the U.S. response, but the U.S. Moon landings, but the Soviet Union's approach to doing anything like this was, extreme secrecy. And we in the Western world didn't learn a lot about what the Soviet Union's response to Apollo was until after the Iron Curtain fell in the early 90s, and a lot of this information began to finally trickle out. There's a gentleman named Asif Siddiqui. I think I've got a link to his stuff in here, who is, I would call him the preeminent living expert on the Soviet space program. He's written a bunch of books. His books are great. They are the best primary sources for a lot of Soviet stuff. But basically, the Soviet space program, while we're over here doing Apollo, is in a push-pull war between these two guys. The gentleman on the right you've probably heard of. That's Sergei Korolev, very, very famous chief designer of the Soviet space program. The gentleman on the left, who you may not have heard of, is another chief designer of the Soviet space program, a gentleman named Valentin Glushko. These guys started off liking each other, and over the course of several years grew to become absolute, I hate you, like real hate, like visceral hate. These guys hated each other. Interestingly, the way that the Soviets approached their Apollo response program was almost by taking a Western approach to rocket development and program development, while we on the Western side took almost a centrally planned Soviet-style approach. Over here we had NASA. NASA dictated the designs. We had contractors that built to NASA's designs. It was all centrally managed. Whereas in the Soviet Union, they actually had competing design bureaus, and not just competing like in an RFP type phase. Like, they had competing design bureaus for most of the entire set of Soviet programs, fighting over resources and trying to impress the Politburo with, you should fund me, you should fund me. And a lot of Soviet missions, rather than being advanced planned, were laid on with very short notice, like weeks of notice. Because one of the design bureaus would put a plan together, and it would be like, we want to launch a Voskhod module to commemorate the opening of the tractor factory in Leningrad. And the Politburo would be like, hell yeah, we're launching it. We fly in 2 weeks. It's really interesting to read it. So these two guys hated each other. And what were they fighting about? They were fighting about rocket fuel, because what else are rocket scientists going to fight over? Korolev favored rockets powered by cryogens, and Glushko preferred rockets powered by hypergalls. Cryogenic propellants are things like liquid oxygen and liquid hydrogen. Those are the cold propellants. They're very cold. Liquid oxygen is extremely cold. Liquid hydrogen is extremely, extremely, extremely cold. And they're very difficult to store and transport because they have to be insulated. They have to be kept at hundreds of degrees below zero. They're constantly trying to boil off. You can't leave a cryogenically fueled rocket up on the pad because the propellant evaporates. You have to, if you're going to fuel it, you have to launch it, or then you have to defuel it very quickly. And cryogenics are complicated to handle and expensive. Hypergalls, on the other hand, hypergolic propellants, are easily storable. They don't evaporate. They're fine at room temperature. They don't require insulation. You can tank up a rocket with hypergolic propellants and leave it on the pad for days, for weeks even. They're called storable propellants for a reason. The problem is the chemicals we typically use for hypergolic propellants are murderously toxic and hideously corrosive. So they are incredibly dangerous in the short term. And if they don't kill you in the short term, they'll give you cancer and you'll die in the long term. A rocket burning liquid hydrogen and liquid oxygen produces steam and water vapor as its exhaust. A rocket burning dinitrogen tetroxide and hydrazine produces, red cancer smoke. And if there's an accident, you have to evacuate the entire, multiple square miles around the rocket. So both of these fuels have advantages and disadvantages. Korolev was the more successful in the near term. The Soviet response to Apollo was this gigantic rocket called the N-1, which was originally designed by Korolev to be a rocket to take people to Venus. That was what the Soviet Union was going to use to leapfrog past America to the moon, and it was repurposed into a moon rocket. There's the Wikipedia article about this. You may have to look up N1-L3, November 1-Lima 3. The N1L3 was the all-up design of the N1 rocket with the L3, little lunar. They designed a little lunar lander and everything. This thing was Korolev's dream baby. This is the rocket that this was his Saturn V. This was his dream thing. And they built it and they launched 4 of them between 1969 and 1972, and they all blew up for various reasons. The 5th flight, if they had ever made one, there's every indication it would have been fine. It would have been a success. But Sergei Korolev died before the rocket ever flew. He died in the 60s, and Valentin Glushko took over his bureau, I believe, and came into his own position of power. And as soon as he had the juice to do so, purely out of spite, he canceled the N1. So it's sort of this, lost historic opportunity of this alternate history where possibly the Soviets might have gone on to land on Mars and land on the moon. They had the hardware, they had probably solved most of the problems, but just literally because one guy wanted to piss on the grave of the other guy, they just canceled it. So that's kind of the end of my presentation here. Now I've got a big long list of books that I would highly recommend folks picking up. I'll send this on to Nathan and Greg after to distribute out to the group if you guys want. These are all outstanding books. The 2 on the bottom, Challenge to Apollo and Rockets and People, are the 2 that focus on the Soviet space program. Both of those are actually available on NASA's website for free if you want, although Amazon also sells them bound. All of these are great. And again, I'll pass this on to the presenters so you guys will, and you guys in the group can have these if you want to download. And that is it. I have this little cool Gus Grissom quote to cap everything off with, but we're way over. So Nathan and Greg, I'll toss back to you guys. Let me quit sharing here. And let me see, let me figure out how to quit sharing my screen.
Well, Lee, I'm really impressive amount of knowledge and material, and I just kind of blown away by I kind of like the depth and breadth of it all. I think what I want to
Is my screen sharing still on? My little there it is.
Yeah.
Okay, let me kill it.
I'm going to go ahead and take the risk and allow for people to unmute themselves if y'all want to ask questions. But while we're waiting, I had a question for you. What's the most interesting question you've gotten while giving tours at the Space Center Houston?
I never get to go in depth because there's a limit. There's 10 minutes, right? They bring the tram group in and you got kind of 10 minutes. And I do this by the side of the Saturn V display. I talk a little bit about the engines in each stage. But I never have time to go into the really cool stuff. But every once in a while, somebody asks and I get to, you walk around the back and look at the injector plate and talk about the injector plate issues and the combustion instability. I think the coolest question that people ask is, okay, I'll tell you what my favorite set of questions is, and it's the questions that the Australians ask. There is no group of people who come in and visit the Space Center who love space like folks from Australia. Anybody who has like flown to the United States and is visiting like the Johnson Space Center anyway, like you've already kind of self-selected into a space interested audience. But I swear Australians are nuts about space. They love it because, you know, they all know the story of the Big Dish and how they participated in the Apollo 11 or all the Apollo program rather, you know, receiving the signals and helping being a ground relay station. Those guys love space. I love it. I love talking to Australians and folks from New Zealand when they show up because it's just gratifying to see how much they love everything because I love it. And it's nice to talk to people who love the things you love.
It's awesome. And I guess, how many Australians do you see visiting?
You know, there's always, because I usually go and work Saturday mornings from 10 till 12 or 1, usually until my voice gives out. And there's always at least one tour group of folks who come in. And they always, like, there was a group of Australian blind folks who came in and they had these little koala doodads, and I got one of those. And they're so cool. And they love space so much, and they always have such cool questions. And you know, it's just neat. It's neat. I will be happy to talk to anybody who shows up during a tour and asks questions because it's like you're standing next to this gigantic Saturn V rocket. You can't, even if you don't know what it is, it's like this thing it's you know 370 feet long. It's ridiculously enormous, and it's neat to watch people walk in and look at it. Because everybody goes, because it's huge. Yeah, that was it.
1202 alarm.
Yes, sir.
I had read, I think, in an AIAA 50th anniversary story about Apollo 11 that there was a attack instructions in the flight computer, and the flight computer, when it ran out of storage, selected the higher priority to do instructions, which would have been, for instance, flying the vehicle. Is that your understanding as well? Sort of.
There is a try to find the link to it. There's an article that we just ran on ours, written by a gentleman named Frank O'Brien, who's written some textbooks on the lunar module computer, and he talks a little bit about the internal structure of it, and he talks about it in a pretty accessible way. If you've got just a basic grounding in you know, basic theory of computer science, like if you know what a program is, and you know, like that, you know, the super duper high levels of how a computer works, O'Brien's explanations are really easy. So the guidance computer maintained a list of, like I said, it sort of maintained a prioritized list of tasks that it was expected to be able to roll through every 960 milliseconds. And when it was unable to get through all of those, it didn't really like dump bottom tasks. It simply dropped all execution, started back at the top of the list, and began running them again. And it began to do that until once again it ran out of temporary storage space, and then it flushed, started at the top, and began to run. It wasn't so much that things weren't getting done, it's that things were taking so long to cycle back around to restart that every once in a while, think of it like there was a hiccup, it dropped everything it was doing and started over. But it didn't, there were other additional, more complicated and deeper restart modes that dumped the temporary storage areas, that dumped all the running data, that like blanked the guidance platform. None of that, fortunately, happened. The easy restart, I forget the name of the routine. I think I had it in the presentation. The easiest restart loop was able to fix the issue long enough to where then they ended up progressing past the part of the mission where it was a problem. The load on the computer decreased, and then they were able to land. So it was only a problem for a period of probably, I don't know, 4 or 5 minutes, but it was like the worst 4 or 5 minutes to possibly have it happen.
Sure.
Now,
Yeah.
Apollo 10, you know, they came close to the surface, but then land. How come they didn't have the same alarm in Apollo 10? Did they not get to that point in the flight, or was there a change in the checklist?
They didn't. I don't think, let me see. Apollo 10, they aborted, I think, at like 60 miles up. I think they aborted before The Highgate, I need to go back and look at my little diagram here. Let me see. Oh yeah, no, they busted out from Apollo 10 before I think they got into the braking phase and everything, because the once you start firing your engine and get power descent going, you're scrubbing velocity, and when you've scrubbed a certain amount of velocity, you're no longer at a point to where you can like return because the Apollo 10 lunar module was a little heavier than Eagle. It had more mass. It wasn't designed to land. It was designed to be a test vehicle. They knew going in that like they couldn't land it. It was too heavy. If they landed it, they weren't going to take it back off again. It was simply physically impossible. But the other side of that issue also is that the 1202 alarms, 1201 alarms, they only happened when you flip the radar on at exactly the right millisecond to where when those things are energized, they're hit with out of phase power. There's always a chance. There's a 1 in 4 chance, actually, that at any given moment you flip it on and everything's fine because you happen to hit it right when the signals were in phase. Aldrin, when he activated it, it happened just bad luck that they flipped it on at exactly the wrong moment. The signals were out of phase. And that eventually, when the load rose high enough, triggered the problem. I believe this David gentleman here, you've got your hand up.
Yeah.
I can see that. That's kind of cool.
Yeah. The hand raise feature is good too. Might help keep people muted until they raise their hands if we have problems in the future. Yeah, I'm retired from NASA JSC. One of the great books that you need to add to your list is called Moonlander: How We Developed the Apollo Lunar Module.
Program alarm. What's a 1202 alarm? I don't know. Houston, give us a reading on the 1202 program alarm.
Roger, we got you. We're going at alarm.
Same alarm.
Roger, we're going at alarm.
Okay, 3070. Roger, understand. Program alarm 1201.
Roger, 1201 alarm. Strength high, we're go.
Pretty rocky area. These boulders are as big as cars. You can't land there. Go in the manual. Feet down to 30. Watch your fuel. 330. 300 feet down, 3.5. Fuel's at 8%. Radar's lost track of the surface again. 160 feet, 6.5 down. 5.5 down, 9 forward.
Low level. Low level.
120 feet, 5% fuel remaining. Quantity light, 94 seconds to bingo, 114 to mandatory abort. Down a half, 6 forward.
Down half of 60. Roger. 60 seconds.
40 feet down 2.5.
Stand by for 30. 30 seconds.
20 feet down a half. Same shadow, drifting forward just a little bit. Contact light.
Shut down.
We copy you down, Eagle.
Houston, Tranquility Base here. The Eagle has landed.
Roger, Tranquility. We copy you on the ground. You got a bunch of guys about to turn blue. We're breathing again. Thanks a lot.
By Thomas J. Kelly, the Grumman chief engineer for the LEM. Excellent book on that. So I just wanted to throw that out.
Yeah,
to
absolutely.
the list.
I've heard the book's title before. I know Tom Kelly, or I know who he is. I don't know him. He's not my buddy. But yeah, totally. I would agree. Even having not read it, that anything that Tom Kelly writes about the lunar module is authoritative and probably very, very, very good. So yeah, I'll totally add that to the list here.
Yeah, and a lot of the stories about the area around Houston and JSC and at Rockwell International, where I used to work too. The whole process. I mean, the whole process of designing LEM was very much like we went through on Space Station, actually. We used more computer simulation and less hardware, like plywood mock-up. But other than that, the design reviews and everything was all very similar.
If you guys have a chance, if you have not watched the HBO mini From the Earth to the Moon, the one that I pulled the Apollo 12 clip from, they have an entire episode. It's episode 5, dedicated to the sort of the evolution and design of the lunar module. It focuses on the Grumman workers, Tom Kelly and his guys, and the whole episode is focused on like how they built the lunar module. And it's probably the Apollo 12 episode is my favorite, but like it's an excellent episode. And it gives you a good little capsule picture in a dramatized TV way of the complexity of designing this true spacecraft, this vehicle that would never have to operate inside of an atmosphere and leaves all common design wisdom behind because none of it applies anymore. And it's they had to do stuff like to save weight. There's no seats in the lunar module, which sounds insane. But then you're like, well, but they don't have to, like in the moon, they're on 1/6 gravity. You don't really need a chair. The legs are great shock absorbers. And when you're in 0G, you don't need a seat. So we can save 1,000 pounds of weight by not having 2 gigantic seats in the cockpit. They had to do stuff like that.
There's a whole section in the book about the SWIP, the Super Weight Improvement Program.
Yeah.
They went through trying to figure out ways they could save weight on it. And some of the ways didn't work out so well, like the chemical milling of the structures where they could take out some weight that resulted in stress corrosion cracking, and undersizing wires to lower than normal wire gauge standards because, well, it wasn't going to heat up that much and not going to be on for long. The wires were all breaking when they were installing them just because of how fragile they were, so thin in gauge.
We'll have to pick it up. That sounds fascinating. I've got it written down here. I'm totally going to grab it. I will be, as soon as we get done here, I'm going to hit Amazon and see if I can get it.
David.
Yeah, it's there. Yeah.
David, does the book say what gave them the idea on how to detach the limb from the command module and land?
I don't remember if that was in there or not. It may have been.
Because what I heard, it came from a cartoon. It was a cartoon idea from Fireball XL5. There's the mini Fireball detached from the front of the Fireball and landed, and then reattached in a circular orbit.
That's interesting. Maybe it did. I haven't heard that before, but that doesn't mean it's not true. You actually bring up a really interesting point. There was again, buy this book, because in this book, this is the Cox and Murray book, Apollo: The Race to the Moon. To your point, gentleman whose name says Donna, but I know that's not your name. The choice to have a separate landing vehicle and not like fly to the moon in one big thing, to have like a lunar module that detaches and goes down, that was a very contentious design choice and was the result of several years of discussion on how exactly to do the mission. That's you'll hear this referred to as the Earth orbit rendezvous versus lunar orbit rendezvous discussion, or the mission mode discussion. There were lots of advantages of doing things in lots of different ways, but the eventual design to have, everything goes up on one Saturn V rocket, and you have a command module that stays in lunar orbit and a little lunar module that goes and lands on the moon, resulted in incredible weight savings. And it would have been considerably more complicated to not have a detachable module that landed, because then you'd have to take this gigantic Apollo spacecraft, get it up into orbit, bring it down to the lunar surface, but leave enough fuel in it to lift itself back up again. It's this huge all-in-one spacecraft, and then get it home again. Breaking everything up on all these tiny spacecraft was a huge weight savings, because you could land in stages, you could throw away parts of the lander. The scary part was having to perform that after you've taken off from the lunar surface, having to meet up in lunar orbit with the command module, potentially without mission control support. And nobody had any idea, would we be able to do that? It's a question of very complicated calculus. You've got to, do your orbital mechanics math. Like, can I take off from the lunar surface, figure out with my radar and my equations where the command module is, meet up with it and dock, and can we do it reliably in a way that, because it has to be repeatable. It has to be doable every single time. It can't be like, yeah, we've mostly got it figured out. We can rendezvous like 4 out of 5 times. Like, that's not, you can't go to the moon if you can only do it 4 out of 5 times. So yeah, it was a very pivotal design decision, and the path to that decision is discussed in penetrating detail in this book. This book, actually, I keep holding it up because I happen to have it in the room before we started here. There's a book by Andy Chaikin called A Man in the Moon that was used as Tom Hanks used that for a lot of the basis of Apollo 13 when he was having the movie done. Chaikin's book, A Man in the Moon, focuses a lot on the astronauts and it's probably the definitive book for anybody who wants to find out what the astronauts did during all of those missions, what each mission was like in space. This is the book that focuses about 5% on the astronauts and 95% on the ground controllers and what they were doing and how the missions worked from the ground. And personally, the astronauts are cool, but this is like way more interesting, I think. There's so much good stuff in that book. And one of those things is a discussion of considerable discussion of the mission mode and how it was chosen.
One more question.
Sure.
Lee,
Yes,
you write articles on spaceflight and then computer games. Have you ever, I haven't seen this, but have you heard a computer game where you can be the astronaut for Apollo 11, walk on the moon, or Apollo 13 and get back to the Earth safely?
There is not really, no. Well, you can get, there's an application called, okay, wait, hold on. Let me just look this up real quick because I don't want to get it wrong. There's a program called Orbiter, which is an open source space flight simulator. And it has a plugin module for it called Project Apollo that lets you, Orbiter normally is a shuttle simulator, but this Apollo plugin for Orbiter lets you run Apollo missions with varying degrees of simulation fidelity. So you can put it in easy mode and just sort of like use a joystick and fly around, or you can put it in real mode and use a simulated Apollo guidance computer and actually run entire mission profiles by putting stuff into the diski and stuff. It's not like flight simulator exciting. It's not like, you know, flying through canyons or whatever, but it is like absolutely fascinating. And when you're in the realistic mode, as more and more of the Apollo guidance computer is simulated, and because they're continually updating it even now, it gets more and more, it gets closer and closer to the full fidelity of the experience. And yeah, it's fun to mess with. But as far as like games, like, you know, there really aren't that many, because it's not like traditional piloting. It's not like stick and rudder work. There's a lot of math. Even when you're doing your moon landing, there's a lot of like math and stuff. And it's kind of a two-person operation. The reason why there were two folks in the lunar module, in addition to, you know, just you don't want to send one person into that, was because the workload was so great that it required two people to deal with. You know, Neil Armstrong is in the left seat, or there's no seats. He's standing on the left side, looking out the window, and Buzz Aldrin, the lunar module pilot on the right, isn't looking out the window. He's looking at the instrumentation, and he's calling out. And you can hear this if you listen to air-to-ground transcripts of an Apollo landing. You know, you can hear Buzz is saying, like, you know, down in 4, like 5 and 20, 6 and 2, 4 and 3. He's calling out horizontal and vertical velocities, and he's also calling out a number. He's calling out the landing point designation number. And this was really cool. So on Armstrong's window, on the pilot's window, the commander's window, there is a set of markings that are inscribed into the glass. And there's 2 of them, and they're sort of inscribed offset, like this, I guess. So there's a set of angle markings, and then there's another set of angle markings, the same one, slightly offset. And they're slightly offset so that the pilot can look out the window and focus his eyes on infinity. And the 2 markings, when your eyes are focused out to infinity, overlap each other and become visible in the foreground. And each angle marking has a number on it. And so if the lunar module pilot calls out 27 for the LPD, 27 for the landing point designation, when the pilot's looking out the window, the hash mark where the number 27 is like, oh, it's sitting on top of the ground in the place where the lunar module is currently set to land. So as the lunar module pilot is calling out LPD angles, the pilot is looking out the window, looking through these coincided hash marks, and the number that guy calls out from the right side. You look at where that hash mark is sitting on the lunar surface at that exact moment as you're flying to it, that's your landing point. It's a very intuitive system, but it really does require 2 people, because the workload was so ridiculous. And they're talking to mission control, and they're flipping switches, and they're doing, like, there was a lot of work. There wasn't a lot of, I mean, there was a lot of automation, but there wasn't a lot of like what we would consider autopilot kind of automation. It just wasn't there. There was a digital fly-by-wire system, but it wasn't like, you know, GPS, I'm going to go land here, go. There was a lot of manual work.
Do they have a window like that at Space Center Houston or someplace else where you can actually see what that would be like?
Well, I mean, they have they've got a limb. I think it's one of the test limbs hanging from the ceiling, but you can't really see it. It's like up there. You can see the LPD. Actually, if you go to like Google Images, let's see if I can find this real quick.
What do you think it would take to make one?
LPD. I mean, it just looks like. Just screen share real quick here, if I can find the screen sharing button again. Too many windows open. Boop. Okay. Share. Whoops. There we go. I'll get up here. Get this out of the way. So it looks like this right here. If you guys can see this. Whoops, I didn't mean to click that. This right here. So this is the LEM window, and this is the LPD cross that's sort of inscribed into the surface of the glass. And see how there's 2 of everything, and it's like that so that when you focus through it, the numbers line up. Sort of like, you know, you put your 2 fingers in front of your eyes and you unfocus, and you can make your fingers come together. Same deal with this. They would just use that looking out the window and be like, you know, your LPD's at 32, and you just look at 32, and wherever 32 sits on top of the lunar surface, that's your current landing point. And the commander can adjust that by clicking a little switch up and down if he's in that mode. And there's all kinds of stuff they can do. I forget the question that got us there, but I hope that was really interesting.
Thank you.
Of course.
So on Thursday, they announced 3 teams to do the human landing system for Artemis, and I think everybody's heard of SpaceX and Blue Origin, but Dynetics, I didn't really hear about, but whenever you were showing that picture of the what was it, the pump for the big F9, I noticed on the fence it said Dynetics.
Yeah, they merged with I think they merged with Rocketdyne or bought Rocketdyne. They were in the propulsion mix at the time. That was in 2013. I think at the time, Dynetics was pushing an alternate advanced solid booster, or not solid, but an advanced booster for SLS. And I think that contract has since been canceled, or it was never let in the first place. They were basically trying to design a booster for the Block 2 SLS, the uprated big one, that instead of being based around the ATK solids, the shuttle era solids, it would have had, each booster would have had 2 F1s in it, 2 uprated, rebuilt F1Bs. Same sort of idea as the Saturn V F1, just a modernized engine with far fewer parts and modern construction. And they were pitching that for a while as an alternative to the solids. I may still actually have some of the stickers they gave me. They were calling it the Pyrios booster, Pyrios, named after Apollo's horses. But I don't think, if you Google for it, you may still find some stuff about it on NASA Watch from a few years ago. But as far as I know, the advanced booster thing is no longer a thing, or it's been given to ATK, because ATK gets all that shit.
Based upon your study of the Apollo program and kind of understanding of all the challenges that they had to go through, I know that we've made huge strides in lots of areas, around computers and simulation and additive manufacturing, and just huge supply chains are available now that weren't available then. But of the 3 companies that were selected on Thursday for like the first round of contracts, which ones do you think are going to have an easier time of making it to the next round?
I don't know. That's a really good question. That would be a question for Berger, my coworker Eric Berger. He's all over that. I'm more the old space guy. He's the new space guy. My personal opinion is that all of those companies are positioned for success. I'm sad that Boeing wasn't included, and I'm partially sad because my wife still works for Boeing, so Boeing kind of pays my mortgage. So it would have been nice, but at the same time, their bid was technically unimpressive, and they were eliminated early because they suck. I mean, Boeing has not been bringing its best foot or its best game to any of the stuff. They're not doing as good as they should be. It's a terrible time for them to not be doing great, because they're also sucking it on the commercial side of things too. The 737 is collapsing, and it's just not a great time to be at Boeing. Out of the 3 that are in there, here's the thing. I think that there's a limited amount of time for these contracts to accelerate into being solidly let, because a lot of these are being driven by Jim Bridenstine, which is great. I like Bridenstine. I've met him a bunch of times. I was initially very concerned about his selection as administrator, but he's proven to be a very agency first kind of guy in a way that I find refreshing. I don't necessarily agree with everything he's doing, but I think his approach towards commercial space and his approach towards the lunar return is the correct approach. I think he's doing a great job. And I think that in that context, Bridenstine very much likes SpaceX. With reason. I mean, Elon Musk is going insane right now anyway, but Elon seems to be holding most of his insanity on the Tesla side of things. Like, he's losing his mind on that side. But for the SpaceX side of things, he seems to like take his insane hat off and become a normal person who knows how rockets work. So, I think that because we have a limited amount of time for Bridenstine, I believe, to continue to push his programs forward. Because if the election happens in November and the Republicans are out, Bridenstine's out. And if that happens, I think there's going to be a tremendous upset in how the programs are working So fast movement is essential. And out of the companies that landed these current set of initial contracts, this exploratory $1 billion, SpaceX is the one that can move the fastest. SpaceX is the one that doesn't have the long tail of legacy aerospace, because even Blue Origin is partnered up with a lot of the old space names, right? SpaceX is the only company in there that is not afraid to iterate very quickly. And if you read the down select document, that gets discussed in detail as one of the reasons why SpaceX was brought into this. Now, their piece of the pie is relatively small. I think they got like $138 million or $150 million. They got the small piece, but they don't seem to really necessarily need the big piece in order to make the impact that they're making. So again, long answer to your question, sorry. I think probably at this point, my personal opinion is that SpaceX is most correctly positioned for success here in the near term.
And regarding the awards, two comments, one serious and one funny. The serious comment was, Jim Bridenstine said that the award amounts do not reflect a preference, but reflects kind of how much the companies need it in order to continue with the thing. So like you were saying, SpaceX really doesn't need, I mean, they're going to develop the Starship regardless, or as long as Elon's able to. Mm-hmm. So, really don't need much motivation. But the humorous comment was about the relative size of the different landers.
Oh, yeah.
I think that the numbers reflect basically the number of pixels an astronaut makes up in each of those.
That's funny, because yeah, that Starship is honking huge. Does anybody have any additional questions? I'm happy to answer them. I know we have passed the 4 o'clock mark, and some of y'all may have somewhere to be. I actually probably have to blow in no more than 30 minutes. But if anybody has any additional questions, I'm happy to take them before we break.
Are you still giving tours at Johnson?
I will be once the Space Center opens back up. The latest that I heard from that was I'm on the email list from the Space Center Houston guys, and they are thinking the center will be closed. The visitor center, Space Center Houston, will be closed at least for another month. But the stuff that I do, the Saturn V tours, is also dependent on JSC reopening, because Rocket Park's on.
Yeah, Rocket Park is on the JSC side. Yeah,
and JSC hasn't publicly announced what their transition back to full operation plan is, and I don't know if it's going to be this summer. I don't know what the agency is going to do, but from what I'm hearing, just from like folks that I know who work there, is that we have some time left, probably a couple of months.
Yeah, I have a tour tidbit for the Rocket Park. If you haven't heard about the Apollo 13 logo, Apollo 15 logo, sorry. Do you know where the hidden 15 is in the Apollo 15 logo?
No, I may not.
It's hidden. It's a Roman numeral XV.
Mm-hmm.
Formed with the outlines of the craters, the edges of the craters.
Really?
Look for that next time. And the clue for it is that the lighting of the craters is all from one direction, except for one rim. For one rim, they had to light it from the other direction, which is not physically possible.
Right. All right, I'll totally look for that.
X of the XV, it's lit from the wrong direction. So look for that next time you're looking at the Apollo 15 logo.
That's fascinating. I will look for that.
Well, great. If anybody has any more questions for Lee, y'all can send them to me, and I can send them off to him, and we'll get them back. But Lee, I think probably now is a good time to go ahead and wrap up the meeting. And I just want to tell you on behalf of all of us that it was such a treat to get you to come and share this wealth of knowledge that you've accumulated and organized and presented in such a compelling way.
Thank you. I appreciate that. You guys were a great audience. This was fun. I'll talk about space all day long. You've heard my main big presentation though, but if you guys want to do another one about the rocket stuff, I'm happy to always come back.
Well, sounds good. I think with that, I think we'll go ahead and end the meeting. So thank you all very much, and look forward to seeing you all next month, possibly in person, but we'll figure that out later in the month. Bye.
Bye. Bye, everyone.
Great. It was great. Thanks.